Alright, so we have been so far discussing properties of continuous functions, or in other words, we have been studying the class of continuous functions. Now in this new section, we are going to see a new class of functions, the class of monotonic functions. Although it's a new class, but its properties are also somewhat similar to those of continuous functions. So let's start the section with the definition of monotonic functions. Let x be a subset of R and f be a real valued function on x. That is, we are starting this definition like how we usually start things in single variable real analysis. F is a real valued function with x as its domain, where x is some subset of R. We say f is monotonically increasing if f of x is less than or equal to f of y for all pairs of elements x and y in the domain such that x is less than y. There is no point in considering x less than or equal to y, because if x is equal to y, then since f is a well-defined function, f of x will be equal to f of y. There is nothing surprising or there is nothing to say about that. Okay. So we take two elements x and y which are distinct in the domain such that x is less than y, and we see that f of x is also like that, less than or equal to y. This possibility of equality is kept. Okay, it may happen and it will happen if the function f is not 1 to 1. Then for two distinct points, f values will be equal. Okay, so that possibility is there. Now if this condition continues to be true for any two such points x and y in x, then we call f monotonically increasing. Now to make this simple, you just think of what the word increasing means. Increasing means that f values are increasing. In what way are they increasing? If you think of perhaps this is the easiest way to understand the situation. If you think about the graph of the function f, for the sake of simplicity, say the domain x is some open interval lying here on the x-axis. Then the graph of such a function, a monotonically increasing function, will in general look like this. That is, for some pairs of x, y values, the corresponding f values are same. And for some pairs of x and y values, the corresponding f values satisfy such an inequality. That is, to put it even more simply, as we traverse along the domain x from the left side to the right side, then the graph either stays at the same horizontal level or it increases. Okay, so that's how the graph of a general monotonically increasing function looks. Similarly, we say f is monotonically, I can write here, decreasing if f of x, if the opposite inequality is taken, is greater than or equal to f of y for all x and y in x such that x is less than y. So correspondingly, the graph of such a function, a monotonically decreasing function, in general will be like this. Okay, as you again traverse along the domain from the left side to the right side, the graph goes like this. It may steadily go down also, that possibility is also there. We are going to talk about that next. Okay, the definition is not over yet. So at some places, in some regions, the graph may actually be a straight line horizontal, okay, parallel to the x-axis. There, this inequality becomes equality. But for some pairs of input points, actually we have a strict inequality. So that's the monotonically decreasing function. Now, if for all x and y in x such that x is less than y, we have f of x strictly less than f of y. This is not exactly the same condition as this. Here we have strict inequality. If this happens for all pairs of distinct points, then f is accordingly called strictly monotonically increasing. It's a special case of monotonic increase. Then f is called strictly monotonically increasing. Similarly, if f of x is strictly greater than f of y for all x and y in x such that x is less than y, so you see that this one is the strict version of this type of inequality. Then f is accordingly called strictly monotonically decreasing. So you can understand that the graph of a strictly monotonically increasing function does not have those parts where the graph becomes horizontal. No, the graph, of course, there may be, in some places the graph is increasing more rapidly, in some places it's increasing less rapidly, but in every region inside the domain it is steadily increasing with no such two values ever being equal if the inputs are not equal. Okay, it is steadily increasing. So the graph is like something like this of a strictly increasing function, strictly monotonically increasing function. And similarly, the graph of a strictly monotonically decreasing function steadily goes down with possibly different rates of going down in different regions within the domain. And there is something else also. If a function is either monotonically increasing or monotonically decreasing, then without say we have not specified which one among these two it is. Okay, it is either monotonically increasing or monotonically decreasing, then such a function is simply called monotonic. Similarly, if it is either strictly monotonically increasing or strictly monotonically decreasing, then it's called strictly monotonic. Now let us see one example. Am I already running out of ink? Actually no, I cleaned the board today, and whenever this is done, for some reason more and more ink is needed. I don't know exactly why. And also it becomes very difficult to rub off the stain. In this example, the author considers the ordinary well-known square function, but in different parts of the real line, thus creating examples of monotonically increasing and monotonically decreasing functions. So he considers the ordinary square function. Now, of course, simply giving such a formula does not specify a function fully. We need to also say what the domain is. So that thing is coming. This is strictly monotonically increasing on the set of non-negative real numbers, which if one wants, one can verify. We will do it, okay? In fact, the author also asks why, exactly why that is so. And that same, I should not say same function, but the other corresponding function is, this is a long thing to write. Let me just write in short like this: strictly monotonically decreasing on the set of non-positive real numbers, that is the real numbers which are either 0 or negative. Why? How exactly? To verify that, of course, you apply the definition. Say I take, first let me consider this one. I take two non-negative real numbers such that x is less than y. Alright. Then from the usual laws of order, uh, I get x square less than y square, and that just gives me f of x less than f of y. So if this is the domain, then the function is strictly, see, we have the strict inequality, strictly monotonically increasing. But what happens on this side? So now I take non-positive real numbers such that x is less than y. Then what happens? Okay, this is becoming a mess. I do it as nicely as I can, but it will still look bad. Just ignore these smudges. Note that both of these are negative real numbers. I mean, of course, one of them may be zeros. I mean, this one may be 0, but one of them is negative. So to avoid confusion, what we do, because you see, when we have positive real number on both sides, we can then take square like how we usually do. But with negative real numbers, we may get confused a little. So we can make this positive by multiplying by minus on both sides. But whenever we do that, because when we have positive real numbers and there is an inequality between them, then we can take square on both sides as usual. So to do that, we multiply on both sides by -1. But that changes that reverses the inequality. And then now we have positive real numbers. Okay, let me just say it correctly. Here we have non-positive real numbers. That possibility of y being 0 is there, it may be there. So here we have non-positive real numbers, but after multiplying by -1, we have non-negative real numbers. And now we can square on both sides. And the inequality will not be reversed. But we also know that minus x square is x square and minus y square is y square. So we have this instead. In place of this, now we have this. So that's why this second function, I should actually call it another function, because you see, although the rules for the two functions are the same, but the domains are different. So technically they are different functions. So this second function is strictly monotonically decreasing, what we are stated here. So that's how this is true. But a quicker way of seeing why that is the case is to just simply draw the graph of the square function. You know that it is this parabola which opens upwards and it passes through the point 0, 0. So what is the set of non-negative real numbers? It is the right side of the x-axis including the 0, including the origin. And on this side the graph is steadily increasing. So that is why it is strictly monotonically increasing. Whereas on the negative side including 0, the graph is steadily decreasing. That's why it is strictly monotonically decreasing. So that way we can see it. Of course, if someone asks you to prove this, this cannot be a proof. Why? Because to draw the graph itself, you need the rule for the function and everything. You need to know what its domain is. So you always have to prove analytically, not geometrically like this, because the geometric graph is coming only from the definition. But to see for yourself why it is true in a quick manner, you can take the help of such graphs. Now note that because of this fact, this is not monotonic on the entire real number, or not strictly monotonic on the entire real number, because on the entire real number we do not have a consistent behavior. In some part it is decreasing, in some other part it is increasing. Note one more thing, that if a function is strictly monotonically increasing, then also by definition it is monotonically increasing. However, not necessarily the converse is true. The converse is not necessarily true. Now, instead of this square function, if you consider the constant function 6, then this is both monotonically increasing and monotonically decreasing on any subset x of R. Why is that so? You see, the condition for monotonic increase is that when your inputs are in some order, say x is less than y, then the corresponding outputs should also be in that order, but there we need not have strict inequality. We have f of x less than or equal to f of y. That possibility for equality makes this monotonically increasing. If you really want to get down to the details, this is why. You just follow the definition. You take x, you see, I don't really know what x is, but it does not matter also. I take x and y in x such that x is less than y. Now, does that imply f of x is less than or equal to f of y? Yes, because actually f of x is 6 and f of y is also 6, and 6 is less than or equal to 6. Actually it's equal to 6, but this is true, this relation is true. Note one more thing carefully, that this is true even when x is the empty set. Why? Because if x is the empty set, then the hypothesis of this implication is false. So the implication is vacuously true, but true nonetheless. So that's why in any case this is monotonically increasing. But because of this same reason, because we have equality, we at the same time have this as well. So that's why it's also simultaneously monotonically decreasing. But it is neither strictly monotonically increasing nor strictly monotonically decreasing. Strictness is there nowhere in the graph of this function, because the graph is just the line y equal to 6, the line that is 6 units above the x-axis and parallel to the x-axis. There is no increase or decrease in nothing. It's just constantly 6. So there is no strict increase or strict decrease. There will, however, if you want to really get strict increase or strict decrease, in one case that is possible. Actually, there are two cases in which even this function is strictly monotonically increasing as well as strictly monotonically decreasing. One of them is when x is empty, because in that case this implication and this implication are both vacuously true. You see, the conclusions of these two implications are false, but we don't care because the hypothesis is false, and if the hypothesis is false, whatever the conclusion is, whether true or false, the implication is vacuously true. And there is another case in which also that same thing happens, but for a slightly different reason. If x is a singleton set, then also the hypothesis of this implication is vacuously true, because if there is only one element in x, then you will not get this situation in spite of x being non-empty, because you cannot find two distinct elements. So the hypothesis is again false, and that's why the implication is vacuously true. So in those two cases, if x is the empty set or any singleton set having only one element, this constant function in this very strange way is monotonically increasing, monotonically decreasing, strictly monotonically increasing and strictly monotonically decreasing. Now, these two classes of functions, that is the class of continuous functions and the class of monotonic functions, it's not that one of them is contained in the other as a subclass. There are continuous functions which are not monotonic. One example is this. This function fx equal to x squared on R is not monotonic. It is neither monotonically increasing nor monotonically decreasing. And at the same time, there are monotonic functions which are not continuous. One such example is this. A simple example. The rule for the function is, say this. And if x is 1, if x is positive, you should understand that positive but less than or equal to 1 and non-positive but greater than or equal to -1. Now this, why is this function monotonic? It is in fact monotonically increasing. Why so? To see that quickly, you just see what its graph is. The domain is this, -1, 1, and say you have 1 here and -1 here. So what the function says is that when the input is less than or equal to 0, then the output is constantly -1. So on that part, the graph is this horizontal straight line, which will have both its endpoints. And if the input is positive and less than or equal to 1, then the function takes the value constantly 1. However, this part does not touch the y-axis. Unlike this part, it does not touch the y-axis. So that's why we are drawing that. This is how we usually draw such figures. That small white circle, in order to keep this part from touching the y-axis. And it of course reaches this point, which is the point 1, 1. So from the graph you can see that the function is monotonically increasing, not strictly, but it's monotonically increasing. The graph stays constant like this, and then suddenly it increases, and then again it stays constantly 1. But it of course is not continuous, unlike that one. That one is continuous but not monotonic. This one is monotonic but not continuous. But what if a function is both? It is both monotonic as well as continuous. In such a case, can we say something about the function that we already have not said? Yes, we can. And the next result is about that proposition. Okay, this part is going to look so ugly. Perhaps I should use this part instead. I don't really know why this happens, these smudges. These will go after I write 2 or 3 times, but the first time I clean the board, this is how things are. So let me just, on this side itself, let me just state that proposition. So what this proposition says is that, say, A and B are two real numbers such that A is less than B. Now let f be a real valued function with the closed interval a comma b as its domain, and this function is strictly monotonically increasing, and also continuous. This is our hypothesis. Then the theorem says that then if maps or let me just use the word bijection itself. I think that's how the theorem is stated. Is there a bijection? Yeah. Then f is a bijection from a comma b, of course it is f's domain, to the closed interval f of a comma f of b. You can already see something, that because the function f is strictly monotonically increasing and a is less than b, so f of a has to be strictly less than f of b. So this is a non-empty, non-trivial closed interval, and f is a bijection from this interval to this interval. In other words, f is a one-to-one function from this interval onto that interval. Now, being a bijection, f will have an inverse. The inverse of f we are talking about, of course, the inverse from this to this is also just like f, strictly monotonically increasing and continuous. So this is the theorem. If our function is SMI and continuous, then it's a bijection from the domain to this interval, and being a bijection, it has an inverse, and the inverse also has those properties. And for the proof, we are going to see which exercise 4. So we will prove it there itself. Okay. And there is also a similar statement which involves a strictly monotonically decreasing function. When we will prove this, there itself we will discuss the other version, the decreasing version. And finally, there is one more example with which the section ends, I mean the theory part ends. And that example is like this. I can write that example here itself so that I don't have to rub off anything. Let n be a positive integer and r be a positive real number. If we simply write n greater than 0, then although we usually use n to denote integer, but strictly speaking, that will simply mean that n is a positive real number. So that's why we need to say specifically that n is a positive integer. But this simply means that r is a positive real number. Since the function fx equal to x to the power n is just like the square is strictly increasing on the positive side of the x-axis, no matter where the domain lies, I mean what the domain is. If it lies on the positive side of the x-axis, then just like the square is strictly monotonically increasing, so is any nth power for any positive integer n. So since this is strictly monotonically increasing on the closed interval 0, r, because of that we can apply this proposition to this function. Oh, and keep in mind that this function, being a polynomial function, is continuous. It's a monomial actually. So we can apply that proposition here. Proposition (983) implies that f is a bijection from 0, r to 0, the nth power of r. And that's why this function has an inverse, and that inverse can be used to define the nth root of a positive real number. You see exactly how that function will take inputs from here, that inverse function of f, and it will give you output here. In particular, because that inverse function is also going to be strictly monotonically increasing, and continuous of course, but we are concentrating on this part, strictly monotonically increasing. So that's why for the inverse function, well, we do, okay, what the hell am I saying? We do not need to see any of these properties to say what I am now going to say. F maps R to the power n. So that's why F inverse maps R to the power n to R, or in other words, the nth root of R to the power n is R. So using this fact, we can define the nth root of any positive real number, and this will be an alternative way of giving nth roots of positive real numbers than what we previously did using which lemma 565, where we studied laws of exponents. If you recall those things, there we had a result itself where we established existence of nth roots of positive real numbers for any positive integer n. Instead of doing it like that, we can use this theorem like this. And before I end this video, there is something else I think I forgot to say. It is that although monotonic functions have many properties similar to continuous functions, like continuous functions satisfy the maximum principle, right? In a closed bounded interval, if we have a continuous function, then it attains a maximum somewhere and a minimum somewhere. That result is also true for monotonic functions, even when they are not continuous. I mean, of course, if a function is continuous, then already the previous theorem applies and we get a maximum somewhere and a minimum somewhere. But if the function is not continuous but monotonic, then also such a result is there. However, intermediate value theorem is not true. So these things we will see in the exercises. So that's just it for tonight. Our next upload is this coming Tuesday. So see you on Tuesday. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.